So regarding the XOR gate, as we mentioned, it is a new gate. We never studied before. So as we usually do for any new logic gate, we have to learn three components. We need to know what's the gate symbol, how to represent it as an equation, and what is its truth table. So as usual, here we are listing all information about our new gates. So definitely here we are discussing the XOR and XNOR. They are actually kind of twins, two sister gates. Okay. Name XOR. And the name XOR comes from exclusive OR, which gives you an indication that it has kind of some similarity with a regular OR gate. It has also counter or twin or negated one, which is called the XNOR gate, which is actually a not XOR. As we usual, for any logic gate, we need to learn actually three things. We need the gate symbol, we need to learn the equation, we need to learn the truth table, the TT. Okay? Now we will start upside down. We usually put the logic gate symbol, but we first want to understand what is a XOR. XOR gate means exclusive OR. What does it mean by exclusive OR? As we mentioned, it has some similarity with the OR. What's OR is doing? OR means I have two inputs. Either of them is true, the final evaluation will be true. So if I have A and B, 1 and 0, so the evaluation will be 1. 0 and 1 will also be 1. 1 and 1 will also be 1. Okay? Only the case where X and Y or A and B, the two inputs are zeros, this is the only case for 0 for the OR gate. The exclusive OR is actually telling you that either me or you, but not both of us. Either me, you, but not both of us. That means it is very similar to the OR. In which sense? If I have the inputs A and B, okay, so these are actually the inputs, and I have the outputs. If both A and B are 0, the output will be 0, similar to the OR. If I have B1, A0, okay, this will be 1, similar to the OR. If I have 1 and 0, the output will be 1, similar to the OR. So in 3 cells, it is similar to the OR, except for the last cell. The exclusive OR, if you have 1 and 1, you have a 0 as the evaluation, which makes the exclusive OR different than the OR. So instead of 0, 1, 1, 1, you have 0, 1, 1, 0. Okay? Which means exclusive OR or XOR. How can I draw the gate symbol for the XOR? The gate symbol for the XOR is drawn similar again to the OR, since it is originated or it has very similarity to the OR. So we draw it similar to the OR, okay? But we add one extra curve here to discriminate make it different than the OR. So I have here A and B, this is C. So this is how can I draw the XOR gate. Regarding the equation, again, here I have C equals to A, B, and I need an operator. We use the plus for the OR. We use the dot for the AND. And since the XOR has similarity with the OR, so we actually put a plus, but we add a circle around the plus to make it XOR, not an OR. The OR is just plus. The XOR is a plus surrounded by a circle. So make it a XOR. Right. As we mentioned, this has a twin brother or twin sister, whatever you call it. Okay, its sister gate is it's directly the opposite operation gate. It's called what? XNOR, and XNOR is actually, so like I have the relationship between AND and NAND, OR and NOR, I have also XOR and I have XNOR. Accordingly, since it gives me the negated logic of the XOR, I expect to see the TT reflect that. A, B, and C. So B is 0, 1, 0, 1. A is 0, 0, 1, 1. Now XNOR, I have 0, 0 will be 1. 0, 1 will be 0. 1, 0 will be 0. And 1, 1 will be 1. Exactly the opposite of the XOR. How can I draw this circuit? As we did for the NAND and the NOR, one drawing for this is to draw it similar to the XOR, but with a circle in front of it. Okay? Again, for the equation, C equals to A, XOR B, and put a bar above all of that. So this will actually indicate that I have an XNOR gate, not XOR. Interestingly enough, people actually also can build a relationship between the AND and the XNOR. Do you still remember the TT for the AND? In, out, A, B, C, 0, 1, 0, 1, 0, 0, 1, 1. So the AND is, do you still remember? 0, 0, 0, 1. If you look at the AND and the XNOR, you will find that similar to the relationship between an XOR and the OR, I have a similar relationship between the AND and the XNOR. Okay, so actually the treaties are kind of identical in 3 rows. Okay, so it is 1, 1 is 1, like here. 1, 0 is 0, like here. 0, 1 is 1, like 0, 1 is 0, like here. And only when both inputs are zeros, here I have 1 for the XNOR. That's why they actually have 2 different ways to draw the XNOR. You can draw it as an XOR with an inverter, or in some references, they draw it similar to the AND, since it has very similarity with the AND, but to differentiate it from the AND, they put a bar here similar to the bar that they put it here. So these are the only 2 gates that have 2 ways to draw them. Okay, one from one perspective, and the other is from the other perspective. So this is a drawing for the XNOR. Similarly, the XOR has also 2 drawings. I can draw it as if it is an XNOR, but I have to put a inverter in front. Accordingly, I have 2 ways to draw the XOR. I have 2 ways to draw the XNOR. Not only that, also for the equations. Since an XOR has similarity with the and it has two ways to draw it or to write its equation. I can write it as A, B. The operator for and is dot. So you can put dot and circle around it. So this is an XNOR. Okay. Similarly, is the XOR. An XOR can be written as the complement of the XNOR. XNOR is A dot with circle B. This is A dot with circle B bar. These are the only gates that have two ways for drawing and two ways or two equation formats. Okay. Right. Now, the usability. When can I use the XOR and how can I use? XOR can be used in any example that have this phenomenon, that if you need to indicate that only one input should be 1 at any given time while the other is 0, and you want to evaluate with 1, you have this scenario, you can use the XOR. If you have this scenario, you can use the XNOR. However, XOR and XNOR can also be integrated in a large circuit. We will take some examples for using the XOR and XNOR, inshallah, in the following chapter. We will see practical examples of using those two gates. However, in the examples or in the problems, I may have some Boolean algebra equations that contains either the XOR or the XNOR. So the question here is, how can I deal with those situations? Example, let's see. Now I have example. Assume that I have some function that needs to be maybe simplified, or maybe I want to put it on GT. I want to put it on K-map, simplified. I need to change the equation to one of the standard. Any kind of example from any of material for chapter 2 and chapter 3. And while the function itself contains the XOR and XNOR, how can I deal with this situation? So let us see an example for that. Assuming that I have a function f of w, x, y, and z. And here is the equation. So I have w. Can you see this example? I have here function f. It's a function of 4 variables, w, x, y, and z. And the function is given to me through this Boolean algebra equation. The implementation for this contains XOR gate and XNOR gate. Assuming that the question need me to simplify using K-map, or want me to put this in one of the standards, SOP or POS, SOM or POM, many of the canonical standards. Okay, can I do any of my work in Boolean algebra or any work of the minimization on the equation while it contains those devices or those logic gates or those symbols? The answer is no, because actually I cannot use of the properties. Okay, so the equation of f as it is written here, I cannot claim that is in sum of product or product sum. By definition, sum of product sum means have. So for sum of product, I need literals bounded with an and terms bounded with an or. Is this satisfied here? The answer is no. Right. For POS, I need literals bounded with an or and terms bounded with an and. Do I have it here? Not either. So this is kind of a challenge. How can I manipulate a Boolean algebra equation that contains those difficult or tough devices, or those new devices, the XOR and the XOR? And actually, the key for this is coming from the TT of those devices themselves. As we learned in chapter 2, that if you have TT for any function, so you can extract sum of min terms or product of max term for that exact function. Okay, so our knowledge for the canonical formats from chapter 2 will help us in this. If you have an equation that contains XOR or XNOR, I can put a kind of an analogous, okay, representation for those equations from the canonical standards. Can you write from your knowledge of Boolean algebra from chapter 2? Can you write another format for the function C which representing the XOR? The answer is yes. I can write it as a sum of min terms. So for the function C or variable C here, okay, I can write C as sum of min terms from where? From its truth table. And the truth table tells me that this function C has two min terms, allocation of ones. So C can be written as sum of the min term. This is definitely using the designators. This is actually, if I just extended this table to show the designators here, I have here 0, 1, 2, 3. That means that this function C has the designators, the min terms as designator 1 and 2. So C can be written as sum of 1, 2. We also learn the M simplification or the M representation, M1 or M2. We also learn the XY representation. Okay, so C can be written as A. So this term will be A bar B or A B bar. So that means I can put an equivalent for the function C for the XOR as sum of min terms to be A bar B or A B bar. What I benefit from this? I benefit from this. I extracted this complex function, which is the XOR, into SOP, or actually SOM, which is basically SOP. So I can manipulate the equation better. Okay? Is this the only representation that I can get for the equation of C from the TT? The answer is no. We can also represent it as product of max term. So C can be written as pi of product of the zeros. 0 at designator 0 and 0 at the designator 3. So it can be written as M0 dot M3. In equation, I can write as an M0 is A or B, and M3 is A bar or B bar. So another equation for the function is A or B, A bar or B bar. So now we have for the XOR 2 gate symbols and 4 different ways to write its equation. Very rich gate. Okay, 2 complex formats that we cannot manipulate within Boolean algebra, and 2 formats that we can manipulate using Boolean algebra. Okay, so if this question is asking me to put F in SOP, can I put F in SOP right now? Yes, I will use my knowledge here of the alternative equations for C implemented here, as we will demonstrate shortly, inshallah. Fine. The same thing applies on mean on the XNOR. XNOR can be written as sum of mean terms. What's the sum of mean terms for the XNOR? It's sum of the terms 0 and 3. That means I can write the XNOR as A bar, B bar, or AB, okay, as a sum of mean terms. I can also write it as A as a product of max terms. For the max terms for XNOR is at the location of zeros. This and this. So their max terms are A or B bar, ended with A bar or B. Okay? 4 different formats and equations for the XNOR, 4 different formats and equations for the XOR, and these are their keys and these are their logic gates. Now, how can I apply this knowledge, okay, into solving this problem? Okay, right now I know that the first complex term here is W XORed with X. W XORed with X from this format of the equation equals to W bar, if I use the sum of mean terms or sum of product, it's W bar X or W X bar. Similarly, I can replace for Z XNOR X. Z XNOR X is actually, hello? Can you hear me? Okay. So, hello? Okay. So, Z XNOR X, I can utilize any of those 2 formats. So I will use the first one. So it can be written as X bar, Z bar X bar, or ZX. Now, using this knowledge, I can go and rewrite the equation for F, W, X, Y, and Z to be, now it is, for the first term, it is W bar X, W X bar, or Y, then replacing this, Z bar X bar, or ZX. After this replacement of the equation, okay, we are rich. The SOP that no, I take the is this are some term, maybe putting in mean terms for F or product of max terms. Okay, any work I can do it after this step of conversion. Okay, so today we learned what is XOR, what is XNOR for 2 variables, and we learned one full example of how can I use my knowledge of XOR and XNOR in examples. Okay, definitely anything that I have here for this table should be a memorize. Okay, so these are only 2 input, XOR and XNOR. Inshallah, in the next lecture, we will learn how can I expand my knowledge in the XOR and XNOR for more than that. Okay, thank you.